All right, so what we're going to do is start our unit on circuits. And so the very first segment on DC circuits to talk about is just some review of some basic properties of circuits that we talked about last year. The first equation that we generally come across when we start to talk about circuits is Ohm's law. And what Ohm's law really does is it relates voltage or potential drop in resistors to resistance of the resistor and current through the resistor. So it's one of the ways that we talk about how resistors are using up energy within the circuit. We also have a definition of current that it's basically the rate of flow of charge, or the rate at which charge moves through a part of the circuit as a function of time. If you had a function of charge that is a function of time, and you took the derivative of that, that derivative is current. Happens to work out the definition of current. The ampere is actually the SI base unit in charge, that it's actually related to current, not amount of charge. Some other things to point out is we talked about power dissipated by a resistor last year. The way to get power is current times voltage. Well, if you think about what power really is, power is measured in watts, joules per second. What voltage really is joules per coulomb, energy per unit of charge. And what current is coulombs per second. If you multiply joules per coulomb by coulombs per second, you get joules per second, or watts power. Now if we apply Ohm's law and plug in IR for V, you get I squared R. If you take and solve that thing for I, you get V over R. So if you plug V over R in for I, you get V squared over R as power. So some of the units: current is in amps, voltage or potential is in volts, resistance is in ohms, and power is in watts. It's worth pointing out charge in this case would be in coulombs. If you're using those definitions, those units will work very well. So there are two basic types of simple circuits that we deal with. One is what we call the series circuit. In a series circuit, everything is on one continuous loop. So there is one closed loop in the circuit where all the elements of that circuit are on that circuit. If this is a series circuit of resistors, the current is constant through all elements of that circuit. We could find the total voltage of the circuit by doing voltage across all the resistors added up, sum them up. And we can find the equivalent resistance by adding up all the resistances. So that's pretty straightforward. If we deal with a parallel circuit, what parallel basically means is there are multiple paths. In the simple parallel circuit, what that means is that each resistor has its own path that's independent of all the others. In that case, the voltage in all the resistors is constant. You could find the total current by adding up the current through each resistor, so sum up all the currents, and the equivalent resistance follows the formula 1 over equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, so on and so on and so on. So those are some things we talked about last year. We actually derived some of these formulas and where they come from. You pretty much just need to know those formulas and how to figure them out. So let's do a couple of quick simple circuits problems. The first one I want to do is find the current, potential drop, and power dissipated in all three resistors of this circuit. So probably the very first thing that I'd probably do is try to figure out what the equivalent resistance is, because that would tell me what the current in this circuit is. So the equivalent resistance is 90 ohms. If I use the voltage of the battery, 20 volts, divide by 90 ohms, I get the current, 0.222 amps, or 2/9 of an amp. It happens to work out that's the current in all three of my resistors. So I can figure out the voltage in each of the resistors. If I do V equals IR for each one, I figure out the voltage drop in all three, or the potential drop in all three resistors. 4.44, 6.66, 8.88. Once I know voltage drop and current, I can figure out the power dissipated in all three resistors independently. Now if I wanted to figure out the total power dissipated, what I do is just add these three numbers up, the 0.986 plus 1.48 plus 1.97, and you would get the total power dissipated in this particular circuit. So that's how to deal with a simple series circuit. Usually the thing you're trying to find in a simple series circuit, if you don't know it, is the current, because the current's the same in every part of the circuit. Now we're going to take and make it a simple parallel circuit. I want to find the three Same piece of information, current, potential drop, and power dissipated in all three resistors. Now in this case, the potential drop is easy because it's equal to the voltage of the battery. Voltage is in the same in all three, so for all three of these, voltage is 9. Well, if I use V equals IR and rearrange it for I can figure out what the current in all three of these resistors are. 0.1 amps for the 90 ohm resistor, for the 45 ohm resistor, 0.2 amps, for the 180 ohm resistor, 0.05 amps. Now you might have heard the saying that electricity will take the path of least resistance. In this case, the vast majority of this current goes through the path of least resistance. If you look at it, the total current is 0.35 amps. 0.2 of those 0.35 are going through R2, the 45 ohm, the lowest of the resistance. The path of greatest resistance has the lowest amount of current going through it. And that's pretty normal. And we can figure out the power dissipated. IV, 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 we're good to go. We could also figure out the total power dissipated in this circuit by adding those numbers up. So those are some quick, simple circuits that we've done before. I wanted to do a quick review of simple circuits. What we'll do in the next lesson is start to look at what do we do with more complicated circuits.